Today we are discussing one of the very important reaction in organic chemistry, that is Reimer-Tiemann reaction. The reaction is performed on phenols using chloroform and sodium hydroxide. The reaction produces a mixture of orthoformylated and paraformylated product, where orthoformylated product is major product. Reaction is performed in aqueous sodium hydroxide solution. Since reaction uses a mixture of chloroform and water containing sodium hydroxide, the reaction takes place at the interface of water and chloroform. So reaction is never homogeneous. In the last step, acid like HCl, which is aqueous acid, is used to protonate the or neutralize the sodium hydroxide, and during neutralization the OH the phenoxide ion is protonated. There are several aspects of this reaction that should be discussed, and these can be answered if we look at the mechanism of the reaction. One important thing that we should discuss is why ortho product is the major product, what is the function of base and chloroform, and we can answer these questions by looking at mechanism of the reaction. Now the reaction start with chloroform reacting with base. The function of base is to first abstract a proton from chloroform. The proton in chloroform is acidic because carbon is connected to 3 electronegative atom. Now once base abstract a proton, so here the arrow is showing that base, which is OH minus, is taking a proton from chloroform, and then there are electrons in this bond. Electrons in the bond, they will shift to carbon. It produces CCl3 minus and water. CCl3 minus species is stabilized by 3 electronegative atom. If Cl atoms are not connected to carbon, then the negative charge on carbon may be concentrated on it, and that will make a very unstable species. So what Cl does is that it withdraw or it removes some of the negative charge from carbon through inductive effect, and that way it stabilizes the anionic species, and so it is stable. A stable species forms faster, so that is the reason the proton is abstracted easily by base. Now if you look at it, there is a negative charge here. Negative charge may again take the proton from water molecule and forming the reactant. So the step is reversible. The first step of this reaction is reversible because this abstraction of a proton by CCl3 minus is taking the product back to the reactant. So we have to write a reversibility sign here. Now there is another thing CCl minus 3 can do. It can give up a Cl minus. If Cl minus goes out, we produces a dichlorocarbene intermediate, which is electron deficient, plus it produces a Cl minus. The Cl minus can attack this electron deficient species, forming CCl3 minus. So this step is also reversible. So this attack by Cl minus on electron deficient carbon may lead to formation of CCl3 minus again. So step is again a reversible step. Now other function of base is to abstract proton from phenol. Since we are using high concentration of sodium hydroxide, it may be from 10 to 20% in the reaction. So we have large amount of base OH minuses in the solution. So if base abstract this proton, we may get a phenoxide ion. So this is phenol. The left hand side species is phenol, and the right hand side species is phenolate ion. Since you have large excess of base in the solution, so there is a little chance of phenoxide ion going back to the phenol, but that there is always a possibility of phenoxide forming back the phenol. Now, what this formation of phenoxide ion does? Now we have two species. One is phenol. If you think about a phenol molecule, in phenol you have a OH group. OH group we know is electron donating. It is electron donating only through resonance, and when OH group donate electron density to benzene ring, it will increase the electron density on ortho and para position. And since electron density moves through orbital and all p orbital on benzene ring are parallel to each other, so it creates a very little difference in electron density on ortho and para position. So both are activated almost equally. So ortho and para positions are activated by resonance almost equally, but OH group is also a electron withdrawing group through inductive effect. It withdraws electron density through inductive effect because oxygen is electronegative, and inductive effect is distance dependent. Ortho positions are closer to OH group, so OH group withdraws more electron density from ortho position than from para position. So there is greater density of electrons on para position than on ortho position, because ortho positions are losing their electron density to OH group through inductive effect. So when we have a OH group, it activates para position more than the ortho position, right? Because resonance doesn't create a difference between ortho and para position. So para position in phenol is much more nucleophilic. So if a reaction takes place on phenol, then reaction may preferably go to para position. So here para position is more nucleophilic than ortho position. Now after deprotonation, what happens? O minus is electron donor group through resonance and through inductive effect. When O minus donates electron density through resonance, it will increase electron density on ortho and para position almost equally, not identically but almost equally. It doesn't create a significant difference between ortho and para position. So when only resonance is applicable, ortho and para position may react almost equally. Now if we think about inductive effect is distance dependent. Now oxygen is rich in electron density when you have a O minus. O minus is electron donor through inductive effect also. So now ortho positions are much closer than para position. So ortho positions are net acceptor of electron density from oxygen, because ortho positions are closer to O minus. So ortho positions are activated more by O minus than para position. So in this particular case, ortho position may become more reactive. So ortho position in case of phenolate ion are much more reactive than para position. And so we have used two factors, one is resonance and inductive effect, to explain why more reaction will take place at ortho position than on para position. Now let's look at the mechanism. Now base has generated a phenolate ion and base has generated a dichlorocarbene. In dichlorocarbene, carbon is a electrophile because it is electron deficient, its octet is not complete, so it is a acceptor of electron density. Now ortho position in phenolate ion are much more nucleophilic, they have higher electron density than para position. One more thing should be kept in mind is that there are two ortho position and you have one para position. So there is a greater chance of ortho position reacting with dichlorocarbene. So ortho positions are much more nucleophilic, so they will react faster with a dichlorocarbene molecule. So attack will take place on dichlorocarbene, producing a species like this. Now this reaction may be irreversible it may be irreversible, and it also forms a water molecule. Why we are saying this is a irreversible reaction? Because a carbon-carbon bond is highly stable. Although CCl2 can, there is a little chance of CCl2 forming, but we may ignore that. Now there is a negative charge on carbon. It may try to neutralize it. What it can do is it can take a proton from water molecule, generating a protonated species and a OH minus. Now this step may also be irreversible, because a OH minus may not take this proton, because that will lead to generation of a negative charge, but there is a possibility. So we may write a reversibility sign here, but we are going with irreversibility sign because reaction is moving in the forward direction. So both these intermediates are non-aromatic in character, so they may try to be aromatic again, because there is a net gain of energy. So that is the driving force. So these intermediate may lose the proton to base. So base will come and it will abstract the proton, generating a aromatic intermediate. Now this aromatic intermediate may be attacked by a base molecule. So this is nucleophilic attack of OH minus. It may attack the carbon. The carbon may be electrophile, because two electronegative Cl are attached to it, and Cl is also a good leaving group. So OH minus attacks carbon, NaCl goes out, generating intermediate having a OH group and a Cl. The hydrogen of OH group may be abstracted by another OH minus, producing a double bond and displacing the Cl as shown here. Now it will produce a formyl group on ortho position, but oxygen will remain a negatively charged species, negatively charged atom. It may be neutralized at the end of the reaction by adding acid. It can be acid, it can be HCl, aqueous HCl, or it can be aqueous sulfuric acid. Any of the acid can be. Now we must think about other ways of this reaction taking place. So we may write another mechanism that may be fundamentally correct. We may take this dichloro methyl containing group, and we may show steps like that. A Cl may go out like this also. This O minus helps in removal of a Cl group, generating a species like this, where there is a double bond between CH group and aromatic compound. It may be attacked by a OH minus. The nucleophilic OH minus is showing its nucleophilic tendency and attacking this carbon, generating this species again, generating the intermediate again. So that may give us reaction. So we may change certain part of this mechanism, but the mechanism should be fundamentally correct. We may, here also we can we may also show that both Cls are replaced by OH group, and then two OH connected to CH may lose a water molecule, generating a formyl group. Para position can also be attacked by para position can also attack the CCl2, which is dichlorocarbene. So para the bond pi electron density near para position may attack dichlorocarbene, which is electron deficient, generating similar species like this, as in case of ortho substitution. Now this negative charge on carbon may abstract a proton from water, generating species like this, and this species is non-aromatic. It may lose a proton to base, generating a aromatic phenolate type ion, and this phenolate type ion again undergoes substitution. OH minus may attack CH, displacing Cl, generating this, as in case of ortho substituted product. The proton of OH group may be taken by a base, generating a formyl group, and then one can protonate the phenoxide ion, forming para product. Now, 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 what is the function of base? There is another function of base. Base not only has a OH group, but it also has a metal cation, and it is alkali metal ion. When you take NaOH as a base, then sodium is the metal ion, and this metal ion is next to O minus. Now, this sodium may also be coordinating on other side to dichlorocarbene moiety, keeping both phenoxide ion and dichlorocarbene together. Now, dichlorocarbene coordinated to sodium may be closer to ortho position, and so ortho position may react preferentially with the dichlorocarbene species. When you change the size of the metal cation from sodium to potassium, the charge on metal ion diffuses, so it may not hold the dichlorocarbene very strongly. So, some dichlorocarbene may go to para position also. Now, if you go to even bigger cation like cesium, the cesium is highly diffused, so it may not be holding a anionic species like phenoxide ion and dichlorocarbene together. So, in solution one may have dichlorocarbene moving around, so which may react with para position. So, when you use a base like cesium ion, you will get more of para product, and ortho para ratio may reach 1:1. So, bigger cation tend to help the para position reaction, and smaller cation like sodium may help reaction at ortho position. So, with this I am ending today's discussion on Reimer-Tiemann reaction. If you have any question, please comment. I will be happy to answer. Thank you.